Okay guys, next we have capacitance of a cylindrical capacitor. Here we have this cylindrical capacitor. It consists of two coaxial cylinder. Like this is one cylinder. Here this is first cylinder. This one. Its radius of this cylinder is A. And we have another cylinder which is given by this one. And it has a radius B. These are coaxial cylinder. Like this line passes through the center of both of this cylinder. This is called coaxial cylinder. We suppose that the length of the cylinder is L. Now let's suppose this inner cylinder is connected to the positive terminal of the battery and the outer cylinder is connected to the negative terminal. Then what will happen? Positive charges produced on this cylinder of radius A, which is given here. This is the cross section. This is the cross section of this cylindrical capacitor. So here this is the cross section of the cylinder with radius A, and this is the cross section of cylinder with radius B. So positive charges induced on this cylinder produced on this cylinder of radius A, and negative charges are produced on this cylinder of radius B. Now to calculate the electric field, we draw a Gaussian surface. So here this is the Gaussian surface, and we assume that Gaussian cylinder, we draw a Gaussian surface in the form of a cylinder. It's like this. This is the Gaussian surface, and this Gaussian surface is a radius R. So this is the Gaussian surface. Now to calculate the electric field of this cylindrical capacitor, we use this relation, which is Q is equal to epsilon naught E into A. But we know that area of a cylinder is equal to the circumference of the cylinder. Circumference of this cylinder is this Gaussian surface. Yes, area of this Gaussian surface, which is in the form of a cylinder, is its area will be equal to its circumference, which is 2 pi r, time its length. The length of this cylinder is L, will give us the area. This is the area of Gaussian surface, and the surface is a cylindrical surface. Cylindrical surface. So the area is given by this one. So if I put the value of A, if I replace the value of A by this quantity, we get Q is equal to epsilon naught E into 2 pi r L. Now from this I can easily calculate the value of electric field, which is Q over epsilon naught into 2 pi r L. I can write it as E is equal to Q over 2 pi epsilon naught or L. Now to calculate the potential difference, electrical potential, we use this relation. V is equal to integral of E into ds, and the path of the integral is this one, from positive plate to the negative plate, or from the positive cylinder with positive charges to the cylinder with negative charges. So limits of the integration are from positive to negative. We can write it as V is equal to integral of this cylinder with positive charges has a radius A, so I put A instead of this positive sign, and this outer cylinder has a radius B, so I put B instead of this negative charge, and we have E into ds. Now E value is already given here. Using this value here, we get V is equal to integral from A to B, and we have Q over 2 pi epsilon naught RL, and we have ds. This is the length element, so I can write it as dr also. ds is equal to dr, because ds is dxi plus dyj plus dzk. So it means that this is also equal to dr, because dr is dxi plus dyj plus dzk. Now all these quantities, this one, this one, this one, they are constant, so I'll keep it outside of the integral. So we have q over 2 pi epsilon naught L into integral from A to B, and we have dr over r. Now this is dr over r, integral of dr over r is equal to q over 2 pi epsilon naught L, and this is equal to natural log of r, ln r, and the limits are from A to B. Now if I put the limits, we get this is equal to the potential, which is equal to q over 2 pi epsilon naught L ln B minus ln A. This can be written as V is equal to q over 2 pi epsilon naught L into ln B over A, by using the properties of this natural logarithm. So this is the potential. Now to calculate the capacitance of this cylindrical capacitor, we use this relation Q is equal to CV, or C is equal to Q over V. Now putting the value of this V from this equation here, we get C is equal to Q over 2 pi epsilon naught L into ln B over A. I can write Q cancel with this Q, so C is equal to 2 pi epsilon naught L over ln B over A. This is the capacitance of a cylindrical capacitor. Here we see that the capacitance also depends on the geometrical factor. The capacitance depends on the length of the cylinder and also on the radii A and B. These are the radii. This is the radius of the inner cylinder, and this is the radius of the outer cylinder. So this is all about capacitance of a cylindrical capacitor. Now next we have to calculate the capacitance of a spherical capacitor. Capacitance of spherical capacitor. Suppose we have a spherical capacitor which consists of two spheres. One is a radius A and the other one has a radius B. Now if this inner sphere is connected to the positive terminal of the battery, and this lower outer cylinder is connected to the negative terminal of the battery, then what will happen? Positive charges appear on this cylinder, and negative charges appear on the outer cylinder. negative charges appear on this cylinder. Now to calculate the electric field in between, in this region, we plot a Gaussian surface. Suppose this is the Gaussian surface. Now this cylinder has radius A, and this outer cylinder has radius B, and I assume that this Gaussian surface, which is a spherical surface, has radius R. Now to calculate, now the path of the integral will be from positive to negative surface. So this is the path of integration. Now to calculate the electric field somewhere on this surface, on this Gaussian surface, we use this relation, which is Q is equal to epsilon naught E into A. Now this is a spherical surface. This Gaussian surface is a spherical surface, and we know that this area of the spherical surface is 4 pi r square. So here I put the area of this spherical Gaussian surface. Now we can calculate the value of E from this equation, which is E is equal to Q over epsilon naught, I can say 4 pi epsilon naught r square. This is the electric field on the surface of this spherical Gaussian surface, which is in between this positive and negative sphere. Now to calculate the potential, we use this relation. For potential, we use V is equal to integral from positive surface to negative surface into E into ds or dr, both are the same. So V is equal to, now the positive surface is a radius A and the negative surface is a radius B. Now E is Q over 4 pi epsilon naught r square into ds is equal to dr. Now this and this quantity, they are all constant, so we can keep it outside of the integral. So we have Q over 4 pi epsilon naught, and the integral is from A to B, dr over r square. If I solve this integral, we get Q over 4 pi epsilon naught, we have minus 1 over r from this integral, and the limits are from A to B. This will be equal to Q over 4 pi epsilon naught into, if I put the limits, minus 1 over r B plus 1 over A. I can write it is Q over 4 pi epsilon naught 1 over A minus 1 over B. Now we can further simplify this equation. So the potential will be equal to Q over 4 pi epsilon naught, and we have, if I take the LCM, is AB, then here we have B minus A. This is the potential. Now to calculate the capacitance of this spherical capacitor, we use this relation. Q is equal to CV, or C is equal to Q over V. Now putting the value of V from this equation, so we get C is equal to Q over 4 pi epsilon naught B minus A over AB. Now Q charge cancel with this charge, so we left with, I can write it here, we left with 4 pi epsilon naught AB over B minus A. This is the capacitance of a spherical capacitor. Here again the capacitance depends on the geometrical factor, like capacitance depends on the radii A and B, radius of the inner sphere and also on the radius of the outer sphere. So this is the capacitance of a spherical capacitor. Thank you.